Welcome to this edition of Models to Ace. Presenting an Excel spreadsheet-based model to derive the optimum sequence for an assignment problem, under given preconditions and constraints. Using linear programming, we will design the model for deriving the sequence of coaches for a presidential convoy, along with the assignment of Secret Service representatives in the coaches. The convoy consists of a sequence of 7 coaches. The slots in the sequence, starting from the first, are numbered 1 through 7, respectively. The 7 coaches are designated Ambulance, Roadrunner, Overwatch, the Hazmat, the Hawkeye Renegade, the ID Car and the Watchtower. The order of the coach names has no relation whatsoever with the order they would occupy after they are assigned to the respective slots in the convoy sequence. Obviously, only one coach can be assigned to a slot. Among the 7 coaches, 3 are of type known as Armored Suburban and 3 others of a type known as Spares. There are 6 Secret Service representatives or SSRs, popularly called agents. They are designated code names: Mayor, Aston, Blue Star, Amazon, Striker, and Roller. The problem involves the task of sequencing the 7 coaches into the 7 slots in the convoy. The sequence is subject to the following constraints. The slot of the Roadrunner, the trailing coach of the convoy, cannot precede that of any other coach. Each of the other coaches must have one of the 6 SSRs deployed in it. All 3 coaches of a type cannot be sequenced consecutively. For example, there cannot be 3 consecutive Spares or 3 consecutive Armored Subs. Overwatch is an Armored Sub and cannot be adjacent to the Watchtower. Blue Star must be assigned to the coach ID Car. Aston must be assigned to the Ambulance due to dependencies on countermeasures. Amazon must not be deployed to the Hawkeye Renegade. The SSR Striker must be assigned to the Armored Sub, Hazmat. Roller must be deployed in the Watchtower. None of the 6 SSRs can remain unassigned to a coach. Roadrunner does not have an SSR deployed. We now set up the model in this spreadsheet in order to solve the sequencing problem. We do this in the tab titled Model, Security Detail. Here, we formulate the assignment problem as a linear programming problem. The model derives 3 sets of assignments. In the first section, the model assigns the 7 coaches to their slots in the sequence of the convoy. This is depicted in the section labeled Sequence Coach Assignment. In the second section, the model assigns the 6 Secret Service representatives to their corresponding coaches. This is depicted in the section labeled SSR Coach Assignment. Finally, in the third section, labeled Coach Type Mapping, the model maps the 7 coaches to the types Armored Sub or Spare. These assignments constitute the decision factors or controlling factors of the model. These are shaded in green as shown here, in the spreadsheet. Since the assignment tables of the 7 coaches to their slots in the convoy, as well as mapping to SSRs, have the list of coaches as the common factor, we place this list in this purple-colored block, here, in the middle, under column I. So, we have the SSR coach assignment section, to the left, here, in columns B through G, while we have the sequence coach assignment section, to the right, here, in columns J through P. The binary matrix, shaded green, in rows 3 through 9, columns J through P, represents a set of decision variables for the solution sequence. This matrix contains an element corresponding to each coach sequence pair. For example, a value of 1 in cell N3 implies that the coach designated Ambulance comes in the 5th slot in the sequence of the convoy. By extension, this also implies that Ambulance cannot come in any other slot. To impose this condition, we create the derived column titled Total, column R, to the right of the sequence coach assignment section. For example, cell R3 contains the sum of all 0s and 1s corresponding to Ambulance in this first row in the decision matrix. Clearly, this sum can have no value other than 1. The same is true for each of the remaining 6 coaches. Hence, column R, under the heading Total, must contain an array of only ones. Another obvious consequence of this assignment of ambulance to the fifth slot is that there can be one and only one such choice regarding the fifth slot, from among the 7 possible coaches. Hence, each column of the decision matrix must contain one and only one value of 1, the remaining being 0. This array along row 11, columns J through P, contains the column-wise sum totals of the ones and zeros in the respective column. For example, this cell J11 contains the sum of these ones and zeros under column J in the decision matrix. Obviously, this sum in cell J11 must be equal to 1 and only 1. Hence, this array along row 11, columns J through P, must contain only ones. All of these 7 ones must add up to the grand total of 7, as shown here, in cell R11. This is the target of our linear programming algorithm. We have given a name to this cell, total sequences covered, using Excel's name manager. Let us open Solver to check how this is set in the objective function. Here, we see that next to set objective, we have supplied the name total sequences covered, which refers to the cell R11, and have stipulated that this must exactly equal a value of 7, here, in objective criteria. Note that this is a redundant objective. If each of the values in the array sequences total across coaches, J11 through P11, has a value of 1, their sum will obviously equal 7. However, we retain this objective, solely for semantic purposes. Next, this binary matrix, shaded green, in rows 3 through 9, columns B through H, represents another set of decision variables for the solution sequence. This matrix contains an element corresponding to each SSR coach pair. For example, a value of 1 in cell C3 implies that the SSR designated Aston is deployed in the ambulance, in the convoy. By extension, this also implies that ambulance cannot have any other SSR deployed to it. To impose this condition, we create the derived column titled Total, column H, to the right of the SSR coach assignment section. For example, cell H3 contains the sum of all zeros and ones corresponding to ambulance in this first row in the decision matrix. Clearly, this sum can have no value other than 1. The same is true for each of the remaining 6 coaches, except for Roadrunner, which should not have any SSR deployed in it. Hence, column R, under the heading Total, must contain an array of only ones, except for the second row, corresponding to the Roadrunner. Another obvious consequence of this assignment of Aston to the ambulance is that there can be one and only one such choice regarding Aston, to one among the 7 possible coaches. Hence, each column of the decision matrix must contain one and only one value of 1, the remaining being 0. This array along row 11, columns B through G, contains the column-wise sum totals of the ones and zeros in the respective column. For example, this cell B11 contains the sum of these ones and zeros under column B in the decision matrix. Obviously, this sum in B11 must be equal to 1 and only 1. Hence, this array along row 11, columns B through G, must contain only ones. The last of the decision matrices, this section labeled Coach Type Mapping, contains the mapping between each of the 7 coaches and its type, armored, suburban or spare. This must be also decided by our model in this binary matrix, shaded green, in rows 3 through 9, columns V and W, representing another set of decision variables for the solution sequence. For example, a value of 1 in cell W3 implies that the ambulance is a spare coach. The column-wise total of all the armored suburban and spare type coaches are captured in these 2 cells, B11, name total armored sub coaches, and W11, name total spare coaches. Overwatch and Hazmat are armored subs. So, the corresponding cells V5 and V6 must have values of 1, denoted by these 2 gray-colored cells, here. Our present problem stipulates that among the 7 coaches, 3 are of the type armored suburban and 3 others of the type spares. Correspondingly, these 2 sum totals must equal 3, which is expressed by these constraint labels in the gray-colored cells V12 and W12. The row-wise total of the assigned type flags for each coach is captured along this column, X, under the label total. Given that a coach can be of type armored suburban or spare or neither, but not both simultaneously, these sum totals must be either 0 or 1. This is expressed by these constraint labels in the gray-colored cells Y3 through Y9. Launching solver, we verify that ranges corresponding to all the three decision matrices, viz. SSR coach mapping, sequence coach mapping and armored sub spare mapping, have been constrained to be binary ranges. In these constraints, launching name manager, we can verify the names of these ranges. Again, launching solver, we can verify that the four arrays of sum totals, coaches totals across sequences, sequences total across coaches, SSR totals across bands are set to be arrays of ones, excluding the total of SSRs against Roadrunner, in cell H4. Also, the two column-wise totals for types of coaches, total armored sub-coaches and total spare coaches are constrained to be equal to 3, each. Also, the values in the array ARR_coach totals across types are constrained to be 1 or 0, by this constraint condition. As a corollary to the model choosing the mapping between each of the 7 coaches and its type, armored suburban or spare in this section labeled coach type mapping, observe that consequently, each of the 7 slots gets automatically associated with the types, armored suburban or spare. For example, as Overwatch is assigned to slot 6, and is of type armored sub, slot 6 gets the unique tag of armored sub. This can be elegantly captured by a sum product between this assignment array of slot 6 and the type mapping array corresponding to armored sub. This is captured in cell O12, here. Repeating this computation for each of the 7 slots, we get this binary array, along row 12, columns J through P, labeled armored sub, indicating whether a slot gets an armored sub or not. Extending this logic to the other twin type spare, we get this binary array, along row 13, columns J through P, labeled spare, indicating whether a slot gets a spare or not. If you recollect, one of the constraints of our problem was that all 3 coaches of a type cannot be sequenced consecutively. This is converted to Boolean logic in these cells R12 and R13, using the binary arrays we spoke about just now. Each of these inner and conditions tests whether the 3 corresponding consecutive cells contain a 1, indicating that the slot is associated with an armored suburban type. This is repeated for each successive contiguous range of 3 cells, extending all the way up to the last sequence of the last 3 slots 5, 6, and 7 along columns N, O and P. The results of all these inner and conditions are ORed in this outer condition to check if even one of these contiguous ranges is of the armored suburban type. Consequently, the value in this cell R12 would be 1, if 3 coaches of the armored suburban got sequenced consecutively. The value would be 0 otherwise. Extending the same logic to the other twin type spare, we get the binary value in this cell R13. Launching solver, we verify that these constraints require both these cells to have the value 0, indicating that all 3 coaches of a type cannot be sequenced consecutively. Extending the same computations of column-wise and row-wise totals to the SSR coach assignment section, we derive these 3 arrays for column-wise totals, armored suburban type mapping and spare type mapping. The last of the derived data sections are these 2 ranges labeled sequence hash, attached to the coach sequence assignment section, under column Z, and the SSR coach assignment section, along row 14. This array attached to the coach sequence section, simply records the sequence number of the corresponding coach, as a consequence of the 1s and 0s placed in this binary matrix, by the model. For example, this value of 1 in the cell N3, indicating the assignment of ambulance to slot 5, translates to a value of 5 in this cell Z3. This can be elegantly obtained by performing this sum product operation between these 2 arrays, the binary array carrying information about the slot assigned to ambulance, and the array containing the exhaustive list of possible slots. Since Roadrunner, the trailing coach of the convoy, cannot precede any other coach, we have this condition constraining the sequence number of Roadrunner to be 7. Since this value can take values only 1 through 7, and an inequality condition has a lesser complexity than a strict inequality condition, we denote this in solver using this greater than or equal to condition. Similarly, we derive this array of sequence numbers for the SSR coach assignment section. Finally, we have this computed value of the gap between Overwatch and Watchtower. This is simply the difference between their corresponding sequence numbers, derived under column Z, made neutral of the positive or negative result of the subtraction operation, using the ABS function. Given that Overwatch cannot be adjacent to the Watchtower, this translates to the condition that this value of the absolute difference of the sequence numbers cannot be 1. This implies that this value must be 2 or greater than 2, indicated in this gray-colored cell C16. Launching solver, we verify that this condition is recorded in this constraint. The remaining constraints are the hard constraints. Mayor must be assigned to the Hawkeye Renegade. So, this cell, B7, named Mayor Hawkeye R, using Excel's name manager, is constrained to be 1. Again, using the logic explained previously, for preferring an inequality over a strict equality condition, we record this using a greater than or equal to condition here, in solver. Aston must be assigned to the ambulance. Hence cell C3, named Aston Ambulance, is constrained to be 1, again preferring the inequality condition over the strict equality. Amazon must not be deployed to the Hawkeye Renegade. Hence, cell E7 is constrained to be 0. Since Blue Star must be assigned to the ID car, cell D8, named Blue Star ID car, must be set to 1. Since Striker must be assigned to the Hazmat, cell F6, named Striker Hazmat, must be set to 1. Since Roller must be deployed to the Watchtower, cell G9, named Roller Watchtower, must be set to 1. Summarizing the details of the model, covered in the Model Security Detail tab, the decision variables are the binary values, in the cells shaded in green. These determine the 3 sets of primary assignments and mapping, the coach sequence assignments, the SSR coach assignments, and the coach type mapping. The objective function, a redundant one in this problem, is the total number of assignments of coaches against slots, which must be equal to 7. The functional constraints, arising due to the particular formulation we have used for the model, are that all decision variables must be binary, there must be only one association between a coach and its slot, and finally there must be only one mapping between an SSR and a coach. The constraints, specific to this problem under consideration, are the hard constraints on assignments of SSRs to their coaches and coaches to their slots, minimum gap between 2 coaches, and constraints on the type of coaches, such as the total number of spares and armored subs and sequencing of a particular type of coaches. Having reviewed the decision variables, the objective function, functional constraints, and the model parameters, let us clear out the cells containing the decision variables. We now launch solver, select the option to make unconstrained variables non-negative, and select the simplex LP method for deriving the solution. We now instruct solver to derive the optimum solution. Solver reports that it has found a solution, where all constraints and optimality conditions are satisfied. This is the set of decision values that solver has generated. The solution suggests these deployments of SSRs to coaches, along with the slots in the convoy, the SSRs get assigned to, as a consequence of the decisions. It provides the mapping of the coaches to the sequences in this section and mapping of coaches against the type of the coach, in this section. Observe that no 3 consecutive coaches of the same type get sequenced together, indicated by the value of 0 in these 2 cells R12 and R13. The model produces 3 categories of decisions, the same as the decision variables. These are the decisions of assignment of coaches to slots in the convoy, assignment of SSR to coaches, and mapping coaches to their types. As a consequence of these decisions by the model, a group of attendant associations gets formed immediately. These are the associations between an SSR and his slot in the convoy, an SSR, and the type of the coach he gets deployed to, and finally, the type of coach in a particular slot in the convoy. The final mapping is automatically reproduced, in a compact manner for easy visualization, in this next tab, titled The Solution, Assignment schedule. The sequence numbers are manually generated in this first column of the table. Data in all the other 3 columns is automatically computed, by formulas, from the decision and consequent cells in the previous tab, using Excel's index and match functions. For example, in this cell C4, we first match this slot number of 1 in cell B4 in this array of sequence numbers, named array SSR sequence, in this range of cells from B14 through G14, on row 14. Having obtained the index of this match, we traverse along this array of SSR names, to the position indicated by this index, to determine the name of the assigned SSR. The same logic is replicated for determining the coach in this third column. To reproduce the coach type, we use a named table of cells starting with the coach names in the first column and ending in the cells indicating coach types. We use the VLOOKUP function to determine the Boolean value corresponding to the coach name. This if function finally converts the Boolean value to the corresponding coach type. These formulae used in the first row are replicated to the remaining 6 rows, simply by dragging the selection of the first row over the remaining rows. Thank you for giving Models to ACE the opportunity to serve you with our analytical models. Please subscribe to our channel for more.